All right, so here we go. You've got your papers. So I'm going to give you 6 minutes. The first thing you're going to do before I answer any questions is you are going to do the 6 basic graphs. There's 4 on the first page, and then the top 2 problems on the second page. So please, as best as you can from memory, you're welcome to look at your notes. This is not a test, but reproduce the 6 basic graphs. Thank you very much. All right, I'm going to get started on the 6 basic graphs. You can check your work with my work. If you have any questions, remember, I love questions. That's why I'm here. That's why they pay me all the Googles of money that they pay me, is to be here and answer questions. So please don't feel like you're an interruption or a bother. You are absolutely not. So I'm just going to do these from memory. You have the tables in your notes, or you can go back on the recording. So the first one is f of x equals x squared. So what this means is for every input, I am squaring. My y value is the square of the input. So if I go over 3, when I square 3, I've got 9. If I go over 2, when I square 2, I've got 4. When I go over 1, I square 1 is 1, 0, 0. When I go back 1, I square negative 1, I get 1. Back 2, square negative 2, I get 4. Back 3, I square negative 3, I get 9. And here is my lovely, lovely, oh yeah, I hit all the points, but the pen failed me. You see that? Come on, pen. There we go. I'm not going to trace over it. I'm only going to make it worse. Okay, so there's your x squared graph. Before I move on, do you have any questions, comments, or concerns about the x squared graph, my parabola? All right, I'm going to move to the right. The next one's absolute value. Remember, the absolute value, what it does is it simply makes everything you put in positive. Okay, so if you put in a positive number, it stays the way it is. If you put in a negative number, it makes it positive. So if I go over 5, absolute value of 5 is 5. If I go over 2, absolute value of 2 is 2. Over 1, 1, 0, 0. If I go backwards, absolute value of negative 1 is 1. Absolute value of negative 2 is 2. Absolute value of negative 3 is 3. And you can do this as many times as you want. It's very relaxing. And so the absolute value is a V. Not too bad. I'm doing pretty good. Before I move on again, any questions, comments, concerns about the absolute value graph? The next graph is my cubic graph, x cubed. So I'm cubing every number I put in. Now the problem with this graph is we don't have a whole lot of points to work with because I haven't given you a giant grid because I am trying to save a little bit of paper. So I go over 2. When I cube 2, I get 8. If I go over 3, I would get 27. So that doesn't fit on my grid. If you have a big piece of graph paper, though, it would work. Over 1, up 1, 0, 0. When I cube negative 1, I get negative 1. Negative 2 gives me negative 8. And you get this graph, looks like a propeller. Oh, yes, I am on fire today as far as my drawing ability goes. I'm loving it. All right, I'm going to keep moving on. If you have a question, just raise your hand. That's what I'm here for. The next one's the square root graph. If you remember from Monday, the square root graph is the first and only of our basic graphs that doesn't work for every x value. You got to start at 0. Square root of 0 is 0. And then I'm just going to pick values that are easy to take the square root of. Don't make this a big headache for yourself. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 6, 7, 8, 9 is 3. And this, if you remember, is just the top half of a parabola that's leaning on its side. So there is my square root graph. I'm going to flip the page to page 2. The next graph's the cube root graph. So similarly to the square root graph, I'm going to pick values that go in, and I can take the cube root of pretty easy. Unlike the square root graph, though, you can take the cube root of anything, positive or negative. So the cube root of negative 8 is negative 2. The cube root of negative 1 is negative 1, 0, 0, 1, 1. And then 8 cube root gives me 2. So I'm going to do my best. Oh, I missed a point. You'll forgive me, though. There we go. There's my graph. And last but not least is my identity graph, my f of x equals x, my line. It just says what you put in is what you get out. So if I put 4 in, I get 4 out. If I put 2 in, I get 2 out. If I put 0 in, I get 0 out. Negative 1 in, negative 1 out. Negative 6 in, negative 6 out. And this function is just a line with slope 1 and y-intercept 0, so nothing too special there. There's the 6 basic graphs. I've just reproduced them quickly. I know that maybe you're not quite that quick yet, but please get to the point where these things become second nature to you. So what I'm going to do now is I'm going to stop for just a moment recording, and we're going to take some time to answer questions. I can start recording, and we're going to share the screen. I might actually be getting decent at all this, but now I've just jinxed myself, so good job. All right, so we've done our 6 basic graphs. Hopefully we're feeling okay about those, or we will feel okay. So now what can we do to any graph, including our 6 basic graphs? So today and on next Monday, we're going to talk about other things we can do. Today, our talk is about translating graphs, meaning translating means to slide the graph. We're not going to change the form of the graph. We're just going to change its position and how we do that in our function notation. So vertical translations. By the way, the word vertical, which direction does vertical mean? Up and down. Okay, so we're talking about vertical translations. Before I talk about vertical translations, up and down, meaning the y direction, let me just ask you a question about notation. When I write f of x, the terminology f of x, that is referring to what value? F of x means the y value. Specifically, it's the y value I get when I plug in whatever x is. So this is my y value. So my vertical translations are going to have something to do with my y value. So here's the definition of vertical translation. If c is greater than 0, just meaning if c is a positive number, then f of x plus c. What I want you to notice is this notation. I'm taking my function, I'm taking my f of x, I'm taking my y value, and I'm adding c, I'm adding some number to the y values. What would you guess happens if I take all the y values of the graph and I add something to all the y values? What's going to happen? All the y values are going to get bigger. It's going to go up. Okay, so that's exactly what this definition says. If c is greater than 0, meaning it's a positive number, then f of x plus c represents a translation up c units. And I'll give you a second to catch up. Same thing, f of x minus c. Well, what do you think is going to happen when I take all the y values and I subtract a number from it? What's going to happen to the graph? All the y values are going to get smaller, meaning a graph is going to go down. So f of x minus c represents a translation down c units. So far, so good. We're going to do a whole bunch of little examples here. So if I don't do enough examples, I've got plenty. So just make sure you're getting what you need. All right. So example 1, I've given us a graph. And what I've asked us to do is to represent this graph in function notation. What is it? Okay. Well, firstly, it's a V. What represents a V? What's the basic graph that I'm representing here? It's absolute value. Okay. So this, I'm just going to write the answer right here. F of x is equal to the absolute value. And what have I done to the basic V graph? It's gone where? Up how many? So what do you think I'm going to put after the absolute value? Bam, you got it. Vertical translation, boom. Hey, Mr. Perkins, is the +4 inside the absolute value or is it outside? It is outside. The absolute value of x represents the y value. And to move the graph up, we're adding to all of the y values. If you're wondering what happens if I put the +4 inside, patience. We are getting there. It's amazing. So what I would like you to do, I'm going to give you 20 seconds. Example 2, same thing. So once again, what's the basic graph we're using here? Absolute value. I tried to keep that part of the example pretty steady. And then what happened to this absolute value? What's its difference? It's down 3 units, so -3. Before we flip the page, so far so good. Anybody got a question, a comment, or a concern? Okay, then flip the page. And so what I've done on the next page is I've just defined 4 graphs to keep things spicy for us. And so we're going to do some examples. I'm going to do one first, and then I got some for you. So we're going to take example 3. This is a non-standard function. In fact, it has a start and a stop point. And so the first thing I want us to do is we're going to do this first one together. We are going to represent what is f of x and then plus 4. F of x plus 4. As you're writing that down, think to yourself, what does the plus 4 do to this graph? It's going to move it up. Okay, so all I'm going to do is to the points that I can see that are defined, I've tried to define a few clearly, I'm just going to move them up 4. So here we go. This y value is 1, so it moves 1, 2, 3, 4. This y value is 4, it goes 1, 2, 3, 4. This y value is 0, 1, 2, 3, 4. This one goes to 0, and then 1, 2, 3, 4. Notice the translation does not change the shape of the graph at all. It's like you've taken a piece of plastic and you've just slid it up 4 units. And so I'm going to connect the dots, and oh, what a lovely graph. Before I give you an example to do, here is a question that I have. What's the domain and the range of, I'm gonna write this off on the side. What's the domain and the range of my original function f? So that the function that was on the copy originally, what's the domain of that? What's the low x value for the original function? -4. What is the high x value of the original function? +4, and since the dots on the ends are filled in. And then the range. What's the low y value of the original function? And what's the high y value? I was super creative when I drew that, wasn't I? All right. Now let's look at the domain and the range of the translated graph, because I want to help you notice what happens, so that if we wanted to know the domain and the range just from the function, if we didn't have the graph, you'd know what to do. So I've moved it up 4. So let's look at the graph. What's the domain now of the purple function? How far left is it? -4. How far right is the purple graph? So notice, when I move the graph up or down, when I do a vertical translation, is the domain affected? No, I've not done anything to the x values. How about the range? What's the low value of the purple graph? What's the high value of the purple graph? And notice we could have gotten that without doing the graph at all, simply by adding 4 to the low end of the range and the high end of the range. That's what I want you to see there, because there'll be a couple homework problems that just give you a function, tell you the domain or tell you the range, and then ask what is the new one. And so without graphing. All right, still doing okay? All right, then here's what I would like you to do. For example 4, which is g of x, I would like you to do for me the same 2 things. First, I want you to tell me, or to graph what g of x -6 is. And then I want you to do the domain and the range of the original graph and the domain and the range of the new graph, please. All right, so the -6 tells me I am going to do what with the graph? Where's it going to go? It's going down 6. So I'm just going to go to each of the points that I've tried to clearly define, and I'm just going to move them down 6. So this point's going to go down to -6. This y value that's at 3 is going to go down to -3. This one that's 0 is going to go down to -6. This one again at -3 is going to go down to -1, 2, 3, 4, 5, 6. Down to -9. And then lastly, this one at 0 goes down to -6. Again, notice we've not done anything in the x direction. We've also not changed the shape of the graph at all. So I know that you probably can't draw as amazing as I can. There you go. Should look, that is actually maybe the best. I should post that on Instagram. That's like the best I've ever drawn. So there you go, at the Perkster if you want to check it out later. Okay, so now domain and range. The domain of my original function. What's the interval of the x values for the original function? Yeah, I seem to be in a rut here, -4 to 4. To fix that. And then the range. What's the range of the original function? -3 to 3. Good. It's not -4 to 4 again. Okay. So now, again, if you need to look at the graph, great. That's why we're doing this, to help you think through that process. If you don't need to look at the graph, great. So we've changed the graph by dropping it down 6. Is that going to affect the domain at all? No, and you can see that on the blue graph. It still goes from -4 to 4 in the x direction. And then the range. If I subtract 6 from -3, I get -9, which you can see that is indeed the low value down there. And if I subtract 6 from 3, I get -3. And again, that is indeed the high value of the blue graph. And that's just the relationship I'm trying to show you. Okay, so I would like you, for h of x, we're going to do the whole thing one more time, just because I want to make sure we're super straight on this. Sometimes students have trouble reading the graph. So for h of x, let's just go ahead and do h of x plus 2. And then, why not? Go ahead and do the domain and range for me, just to make sure we're set. We won't do domain and range on the next one. All right, so I'm just going to get started on this. I'm going to add 2 to all of these values. So up to 1, 2, yep, 1, no. Didn't copy super good right there. So the line's actually right there. And then up to, and then up to right there. And so the graph's going to look something like this. And so and then just like that. Okay. Oh, I got a little messy there at the end. So now my domain and my range. If you're not seeing this, please feel free to speak. Okay. There's no reason to leave here with any questions because I want to answer them all. So the domain of the original graph goes from -5 all the way to 5. And then the range of the original graph goes from -3 up to +3. And then my orange graph, The new one, the domain does not change because we have not moved it in the X direction. That's coming in just a minute. And then the range should be moved up to, so it should be -1 to 5 should be my range. And indeed, the graph bears that out. So last one, you don't have to do the domain and the range of this one. I just want to make sure that we're all straight. I hope that you're feeling like, okay, I really don't need another example. That's kind of my hope and goal in doing a whole bunch of examples. And so this last one I would like you to do, let's do k of x. Oh, the pen is failing me. Let's do k of x, and then let's do -5. We'll see if we can get this pen to work. Oh, I think you're going in the garbage. You're welcome. Here goes. I'm going to take this whole thing. I'm dropping everything down 5. So this is going to go to -5 right here. This point, which is at -3, is going to go down to -8. Then we've got this point, which is going to go down to -5. This one goes down to 1. And then the rest are going to be 1. So the shape of this graph, this one does not have a stopping point. Looks like that. That's vertical translations, covered in detail. Before we go on to horizontal translations, do we have anything you need to ask? Yeah.
So would the domain and range of these be in brackets?
Now on this one, the domain and range of the other 3 are in brackets because I filled in the points on the end. The domain and range of this one would be infinities, and we always use, well, at least the domain on this one is infinities. We always use parentheses at infinities. Okay, so that would be the difference. Great question. Any other questions? Yeah.
So when we're given these on the test, it's going to have like k of x -5. It's going to have that and not just example 6 k of x. Like it's going to give us the number that we know.
Well, I gave it what I was saying, example 6 k of x. I was telling you that the graph that existed already was k of x. So that was me defining the graph for you. And then I said our example is going to be to take that original k of x and we're subtracting 5 from it. Okay, so that's in each of those, the original graph that was there. The first one was f, and then g, and then h, and then k. Okay, great. Yes, if I want you to translate a graph or do anything else, I will define the graph unless it's one of the basic graphs. And we'll talk about that toward the end, how this applies to those basic graphs. Okay, so before we do that though, horizontal translations. Now I need your listening ears on before you get totally bored today and tune me out. This is the part I need you to hear. Okay, so if c is greater than 0, again, if c is a positive number, then this time the notation is going to look like this: f of x plus c. Notice, and if you need to turn back to the previous page to notice the difference, what is the c attached to this time? The x. It's inside the parentheses. It's attached directly to the x. That is your clue that we're talking about a horizontal translation. So notice, just because I want us straight, notice on this, the c was outside of the function notation. This time, the c is inside with the x. Now here is the thing to be careful of. When we do our horizontal translations and when we come back on Monday and we do our horizontal stretching and shrinking, it's the exact reverse of what you would think it should be. It's counterintuitive. And the reason is, I'll tell you the simplest way I can explain it. But what this says, what you would be tempted to say, and I understand when I first learned this, I was tempted to say this. You would say, oh, we're adding c, so I'm going to go to the right. I'm going to go in the positive direction, right? That's what you would think, but what you have to do is unlearn that. When we're doing this, this represents a translation left in the negative direction, C units. Whoops. So it's the reverse of what you would think just by looking at it. It's the reverse of what we saw for the y values. The reason is because negative c, if I plugged in negative c for x, negative c plus c gives me 0. That was what would return the function to its normal. That's why it's the opposite, is because of what the root of this function would be. So if that helps at all, maybe it does, maybe it doesn't, or you might just have to remember when you're doing things in the x direction, it's the opposite of what it looks like. So the same thing, f of x minus c represents a translation so minus c, again, you think automatically negative direction, but no, this time we're going to go right c units. I'll give you a moment to write that down, and then we're going to flip the page and do some examples of our horizontal translations. And then where we're going to end our day is making sure we're clear on this, and we're gonna look at the basic functions, and we're also going to look at doing these two things together. All right, so I'm flipping the page. Example 7 gives us a graph that's been translated horizontally, and we're going to write the function notation for this. So f of x is equal to, well, first off, tell me which of the basic functions is represented on example 7? X squared. Which way has the graph gone? It's gone right. How many units? 4. Okay, so here's what you do. And if you don't, I'm not expecting anybody to have seen or to know this. We're learning today. Remember, the 4 is going to now be attached to the x, so I need some parentheses. And when I go to the right, 4 units, that's the positive direction, so that is x minus 4. Remember, it's the exact opposite of what you think. We've moved it in the positive direction, so it's x minus 4. Please do example 8. Same sort of thing. It's the same function to avoid learning too many things all at once. What is the function notation for this graph? So how many units has this graph been moved? 6 units. Which direction? Left, in the negative direction. So since it's been moved in the x direction, the value is going to go right on the x. And since I've moved it left, it's going to be x plus 6. So far, so good. I know that's sometimes tricky to get a hold of, and that's why we're doing a bunch of examples. So I'm going to do example 9 with you. We're going to take f of x, and we're going to graph. Let me get a different color here. We are going to graph f of x minus 3. And then we're going to, for these 2 examples, we won't do it for all 4. We're also going to do the domain and the range. So f of x minus 3. Notice the x minus 3 is, again, inside with the x. So that means, which way is this graph going to go? It's going to go right 3 units. So in the positive x direction. When I subtract 3, it's going in the positive direction. So here goes. I'm going to take all of the x values, 1, 2, 3. Notice this time we're not doing anything to the y values. 1, 2, 3. 1, 2, 3. 3, 1, 2, 3. There we go. Whee! Boom. There it is. We saw earlier, I'm not going to make you reproduce this. You can look back on the earlier graph that the domain of the original graph was -4 to 4. The range of the original graph was -4 to 4. I'm just carrying that over from the previous page. And now the domain and the range of the new graph. Well, this time, since I've moved it horizontally, I've moved it in the x direction, which one is going to be the one that changes, the domain or the range? The domain. And in fact, we're going to add 3, and we can see that from the graph, or you can do that directly, whatever works for you. But we can see that the lowest x value of the blue graph is -1. The highest x value of the blue graph is 7. And that's what I get if I add 3 to each endpoint of the domain. And since I've moved this horizontally, what's going to happen to the range? It's going to stay the same. We haven't moved it in the y direction, so it's going to stay -4 to 4. Wonderful. What I would like you to do, please, is g of x. I'd like you to please do g of x plus 5, and then do the domain and the range of the new graph. All right, so we have the x plus 5 in parentheses. That means this graph's going to go where? Left. Perfect. Thank you very much. So it's going to go from -4 to 2, 3, 4, 5 to -9. This from -2 is going to go to -7 to -5. This one's going to go to -3 and then to -1. And again, I'm just repeating this because we're going to do something a little different on Monday. Translations do not change the shape of the graph at all. It's like the graph is made of stone and you're sliding it. And so now the domain of the new graph, we can get this either by just subtracting, or you can look at the graph. But when I subtract 5 from -4, I get -9 and I get -1. And then I've not done anything in the y direction. So the range stays -3 to 3. All right, a couple more, and then we're going to finish with a flourish. H of x, go ahead and do h of x. Let's go minus, there's only so many values I have because of the graph size. What have I already done? I don't want to be too boring for you today. Let's do x minus 4. I'm just going to get started with this. You can keep finishing. X minus 4 means I'm going to move the whole thing in the positive x direction. I'm going to add 4 to all of my points. So I'm doing that right now. And when I do that, it looks just like this. I didn't ask for the domain and the range, but if you gave it, it's the domain of this one that is affected, and you added 4 to both the low part of the interval and the high part of the interval. All right, one more of these, and then just a few more problems. You've done great. I appreciate your endurance today. Let's do k of x. Let's go plus 1. Just a little nudge. All right, so on this one, everything's going to go left 1 unit. So left a unit, left a unit, left a unit, left a unit. And so looks like that. And then just like that. And then hard to see, but I'm doing my best. There's the rest. All right, so I've just got a couple more things for us to do. You've done a great job. I really appreciate it. What we're going to do is we're going to do one example each of a basic function, and then we're going to come back to this page, and we're just going to finish with, and it should probably be intrinsic. If you don't have any questions at this point, what happens if both of those things happen together? So if you wouldn't mind flipping back to the front page of your sheet, back to the bottom of page 1. I would like you please to do these 2 things on page 1. I'd like you to do, to graph x, let's go x minus 3 cubed. And then I would like you to please do the square root of x and then plus 4. Notice on the square root of x plus 4, that plus 4 is not under the radical. It's not associated with the x. Okay, this is the notation. Just want to make sure you're familiar with how this is notating. One of the, just a hint, one of those is a horizontal, one of those is a vertical. Okay, I've done one of each. All right, so here's why I want you to get so familiar with these graphs. What you probably did, because you're just learning, and I understand, and this is exactly where I expect you to be, is you've probably taken the graph we've already drawn and you've gone to each of the points and you've gone, okay, I'm going to go right 3, I'm going to go right 3, right 3. But once you get familiar with the graph, what you can do is you can just take this middle point at the origin and move it 1, 2, 3 to the right. And then you can remember, okay, from there, what does the cubic function look like? Well, I can go over 1 and up 1. I can over 2, up 8. I can go back 1 and down 1, back 2 and down 8. Okay, it's a little quicker. So the more familiar you get with these graphs, the more quickly and accurately you can make this cute little sketch. Either way you did it though, it should look like my graph does right there. And then the square root of x plus 4, notice the square root of x is self-contained. The plus 4 is not under the radical, so this is different than if I had written square root of x plus 4. Okay, so please, oh, you can't see it. Square root of x plus 4. Notice this plus 4 is under the radical. That would be a horizontal translation. Okay, so does everyone see the difference? Okay, so that's not what I asked you to do. So this is adding 4 to all the values. So again, 1, 2, 3, 4, and 4, and then 4, and then 1, 2, 3. That copier, I fell for it again. The copy machine did that to me. Okay. All right, if you return to page 5, we're just about done for the day. I should have probably put the graph of f of x onto this. So that's just an oversight of mine. So let me just reproduce f of x. So if you want to, or if you just want to find it from the other page, f of x, we were at -4 and 1. And then it went up to -2 and 4. And then went through 0, 0, I believe. And then 2 and -4. And then at 4 and -2. So that is this point right there. I did not fall for it again. So tell me on this graph, let's just make a note of this and then we'll actually do the graph. I'm now going to graph f of x minus 3 plus 2. So before we do anything, tell me one of the two things. Two things are happening here. What's one of them? It's going to go 3 right. That's the -3. And what else is it going to do? It's going to go up 2. Great. So I'm going to take each of the points and I'm going to go 3 to the right and I'm going to go up 2. So this end point, 1, 2, 3 to the right and up 2, 3 to the right, up 2, 3 to the right, up 2, 3 to the right, up 2, and finally 3 to the right and then up 2. And then here's my new graph. We've done both a horizontal and a vertical change. I'm filling in the domain in the range of f that we had before. So just translating that over from previous times. And then if you want to look at the graph to get the domain in the range of the new one, that's fine. Or if you just want to know that since we took the graph 3 right, then what that means is I'm going to add 3 to the domain. So I'm going to get -1 to 7, which agrees with my graph. And then since I took the graph up 2, I'm going to add 2 to each end of the range. And that's going to give me -2 to 6, which again agrees with my graph. So if you want to reproduce G, I don't know why I didn't do that. It didn't occur to me. So the brain wasn't working that great. If you want to reproduce G on example 14, I want you to do G of x plus 4 minus 6. All right, so what two things happen to the function g right here? Left 4, down 6. Fantastic. So left 4, down 6. The left 4 comes from the x plus 4. The down 6 comes from the minus 6. So left 4, so 1, 2, 3, 4, and then down 6 is going to be, I believe, right here. Left 4, 1, 2, 3, 4, down 6, 3, 4, 5, 6. Good. Left 4, down 6. Left 4, down 6. And then finally left 4, down 6. And again, my graph looks exactly the way it did. The old domain and range of the graph, the domain was -4 to 4, but we went left 4, so I'm going to subtract, and I get -8 to 0, which the graph verifies. And then I went down 6, so I'm going to subtract 6 from each of these, so that takes it to -9 to -3. Okay, so we got about time for one more example. So I'm going to pick one from the last page. We'll also use a couple of the problems from the last page to review when we start next time. So bring this packet back with you. What I would like you to do is go to example 17. Example 17 says, take your basic absolute value graph. And if you need to in light and pencil on there, do the absolute value graph, that's fine. But then after that, do the absolute value of x plus 2 and then -4. Absolute value of x minus 2, or excuse me, x plus 2 minus 4. So if you're not doing anything else, because I know we're doing an absolute value, not one of the other functions, you can at least put the basic function on that nice and light, then that's fine. You can work with that. All right, just for time's sake, because I promised to always start and stop on time, here we go. So again, if you have nice and light, put the absolute value, which is just the v function, that's great. So tell me, what two things are happening to my absolute value function when it's absolute value of x plus 2 minus 4? Okay, we're going left 2 and then down 4. So what I'm going to do is I'm going to take that vertex, I'm going to take the pointy part of the absolute value, and I'm going to move it left 2, 1, 2, and then down 4, 1, 2, 3, 4. And then remember, the absolute value, as you move each space away from that vertex, you go up a space. So I go left 1, absolute value is 1. Left 2, absolute value is 2. Left 3, absolute value is 3. And you can keep doing that. The same thing right. Left and right, I'm terrible with. Right 1, up 1. So then if I go left 1, I go up 1. -2, I go up 2. -3, I go up 3. And you can keep doing that as much as you need to. And you see that your v has been moved left 2, down 1. What's the domain of this? Well, the domain of the absolute value does not change. It's -infinity to infinity. When you add or subtract to infinity, you still have infinity. And then the range, the low value of the range has changed to -4. And then the high value of the range has not changed. It is still infinity. So if you want to take a stab at a couple of those other problems on the last page, that's great. I will pick a couple, and that's where we will start before talking about stretching and shrinking on Monday next. Hope you all have a great, amazing weekend, and I'll see you Monday.